Okay, so let's talk about chemical bond energies and how we're going to use these bond energies to help us predict delta H of reactions. Because really in a reaction, those energy changes are going to be associated with these bonds and how they're broken and reformed, and the energy put in to break the bonds and the energy that comes out when the bonds form. Okay, so initially though, remember, why do atoms bond? Well, it's going to be because of that attractive force between oppositely charged particles. The positive charge of nucleus in one atom is attracting the electrons of another atom. And as they get closer and closer together, they're going to reach a certain energy level that's going to cause them to be stable. So within that bond, we're going to have energy associated with that bond because of this attractive force between that nucleus and electrons. Okay, so the energy associated with those bonds, that's what's going to be responsible for all those heat transfers we see in chemical reactions. That's what's really going on with those chemical reactions. Mathematically, for calculating a delta H reaction using these bond energies, we'd look at the sum of the delta H for the bonds being broken plus the sum of the delta H for the bonds being formed. Okay, now, when looking at this equation, you have to keep some things straight. So when we look at a bond being broken, is that going to require us to put energy in, or are we going to get energy out from that process? Well, in order to break a bond, we have to put energy in. Okay, which means that's going to be an endothermic process, which means our delta H values for those bonds being broken are going to be positive delta H values. When I look at forming a bond, are we going to get energy out, or are we going to put energy in for that? Well, when we form a bond, we're going to get energy out. That's going to be an exothermic process. Since it's an exothermic process, those delta H values are going to have to be negative. It's going to be important that you get these concepts down and that you understand. I have to put energy in order to break a bond. When I form a bond, I'm going to release energy. Remember, forming bonds reaches a more stable state. So to go from a higher energy state to a lower energy state, I've got to release that energy. So forming a bond gives up energy. It's an exothermic process. All right, now, along with these bonds, something that I need to recognize and be able to see initially is something dealing with bond lengths. We have to know the distance between the nuclei involved with these bonds. It's going to help us predict other bond energies and how strong these bonds and how weak these bonds are. Okay, so if I look at just bond lengths here, what are some trends I'm seeing? If I look at the HF single bond versus the HCl single bond versus the HBr single bond versus the HI single bond, what's the trend as I go through those? Well, the trend is the bond length is getting larger. Why? Well, hydrogen's not changing in size, but fluorine to iodine, as we go down a group, that atomic size increases. So fluorine is the smallest, iodine is the largest, so just based upon the atom size indicates we have longer bond length. And that should make sense. The larger the atom, the longer the bond length. Another trend we need to notice. Let's look at the carbon-carbon single bond versus carbon-carbon double versus carbon-carbon triple. What's happening there? Well, the bond lengths are decreasing. So a single bond is going to be longer than a double bond, which is longer than a triple bond. Why? Well, if you think about it, if I look at that carbon-carbon triple bond, in order to form a triple bond, I have to get overlap of 3 sets of orbitals. In order to get overlap of 3 sets of orbitals, I've got to pull those atoms close enough together to do that, which means my bond length is going to be shorter. Okay, so atomic size is going to affect bond length. What type of bond we have is going to affect bond length. All right, so it's important to understand those bond lengths. All right, now we can look at average bond energies, which is the energy associated with those bonds. Whether we're breaking it or forming it, if we're breaking the bonds, we have to put that energy in. If we're forming that bond, we're getting that energy out. Let's look at some trends here. Let's go back to that HF, HCl, HBr, HI. If we look at HF down to HI, HF has got a larger bond energy than HI. In other words, it's going to be harder to break the HF bond than it is the HI bond. Why is that? Well, it goes back to those bond lengths. HF has got a shorter bond length than HI does. HF, the nuclei are closer together. They're going to be closer to those electrons, so it's going to be harder to separate that hydrogen and fluorine from each other because of that. Okay, so the smaller the bond length, the stronger the bond energy. Let's look at the carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. As we go down that group, we talked about how the carbon-carbon triple bond had a shorter bond length than the carbon-carbon single bond. Okay, well, the same trend holds true then. The single bond is going to be easier to break than the triple bond. Partially based upon bond lengths. More importantly, though, is just the fact that if I have a single bond versus a triple bond, well, it should be easier to break that single bond. A triple bond means I have more attractive forces going on. I have 3 bonds formed. That's going to hold those atoms together a lot stronger than a single bond. Okay, so single versus double versus triple. Triple is going to be the highest bond energy, the hardest one to break, just because I've got 3 bonds involved there. Okay, so those are some general trends that we see based upon bond lengths and how they associate with bond energies, as well as single, double, triple, and how they associate with bond energies. Let's look at using these bond energies to actually calculate a delta H of reaction. So let's look at burning of methane. CH4 plus 2O2 goes to form CO2 plus 2 waters. Okay, there's our balanced equation. All right, we want to calculate delta H of reaction for this. Well, the first thing we need to do, we need to know the Lewis structures for all of these to know what bonds we're dealing with. If we can't draw the Lewis structures, we don't know what types of bonds we have. Okay, so if I draw the Lewis structures out for each one of those, I've got one CH4 there with C single bonded to all the hydrogens. I've got 2 O2 molecules. Each O2 has an oxygen-oxygen double bond. My CO2 has a C double bond O. It's got 2 of those. And then I've got 2 water molecules, each containing 2 OH bonds. Okay, so those are the Lewis structures. It allows me to see what bonds I'm dealing with. All right, next I need to determine what bonds are being broken, what bonds are being formed, and what their energies are associated with those bonds. Okay, so I need to consider my Lewis structures in my reaction here. So starting from the left, working my way to the right, my CH4, I've got 4 carbon-hydrogen bonds. The bond energy associated with that carbon-hydrogen single bond is 414 kilojoules per mole. All right, I'm going to have 2 oxygen-oxygen double bonds. The energy associated with an oxygen-oxygen double bond is 498 kilojoules per mole. Those are positive. Why are they positive? Well, because those are bonds that are being broken. Remember, if I break the bonds, I have to put that energy in. It's an endothermic process. I have a positive delta H associated with that. Let's go to my CO2. My CO2, I'm going to form 2 C double bond O bonds. Each one of those is going to be 799 kilojoules per mole. The bond energy associated with a C double bond O is 799 kilojoules per mole. Now, when you look on the table, note there is a difference between C double bond O in other compounds versus C double bond O and CO2. There's a little asterisk on that table. Okay, we're dealing with the CO2, so it's going to be a slightly different value than the normal C double bond O bond energy. Okay, but now, why did I put the negative out in front of that? Well, these are bonds being formed. When I form those bonds, I get energy out. So that's an exothermic process, so my bonds formed side, I have to put that as negative energies. Okay, then my waters. I have 4 oxygen-hydrogen single bonds formed. The energy associated with the oxygen-hydrogen single bond is 464 kilojoules per mole. It's also negative because I'm talking about forming those bonds. So once I figured out the number of bonds I have and the bond energies associated with those types of bonds, I can go back to this equation where delta H of reaction is equal to the sum of the delta H of the bonds broken plus the sum of the delta H of the bonds formed. Okay, so looking at my table here, I now need to take into account, though, my number of bonds that I have. Okay, when I plug those into the equation, I can see I've got basically 4 moles of the carbon-hydrogen single bond, so 4 times the 414 kilojoules per mole, plus I had 2 of the oxygen-oxygen double bond, so 2 moles of that times the 498 kilojoules per mole. That's my bonds broken part. For my bonds formed, it's going to be 2 moles of the C double bond O times the negative 799 kilojoules per mole, plus 4 of the OH single bonds times the negative 464 kilojoules per mole. Okay, plug those in, calculate out my answer, and I get a negative 802 kilojoules. So the delta H for this reaction is a negative 802 kilojoules. We determine that just by looking at the bond energies. Okay. Now let's get a visual idea of what's actually going on in this particular process. Right? So if I look at enthalpies here, and I start with my reactants at a certain enthalpy level, got my CH4 plus my two O2s. Okay, I'm going to have to put energy in order to get those bonds broken. When I break those bonds, I've broken everything up into their atoms at this point, right? So I've got 1 carbon atom, 4 hydrogen atoms, 4 oxygen atoms. Okay, so to do that, I had to put in 1656 kilojoules to break the 4 carbon-hydrogen bonds. I had to put in 996 kilojoules to break the 2 oxygen-oxygen double bonds. So the amount of energy I put in overall to break those bonds was going to be the 2652 kilojoules. So I put that energy in to break those bonds and get everything into just atoms, but those are going to be at a higher energy now. Okay, they're unstable in those atoms form. So what happens? Well, now I'm going to go to my product side. When I go to my product side, I'm going to reform bonds. When I reform bonds, what's going to happen? Well, I'm going to lose energy. Why am I losing energy? Well, those atoms that are at a higher energy level, they're unstable. When I go to that lower energy products formed, those are more stable. In order to go from that higher energy to lower energy, I have to give off energy. Okay? So I go to form my products here. When I form those products, I form 2 of the carbon-oxygen double bonds. The energy I get out of that process is going to be a negative 1598 kilojoules. Okay? I'm then going to form 4 of the oxygen-hydrogen single bonds. The energy I get out of that is a negative 1856 kilojoules. So when I form those bonds then, the overall energy I get out is a negative 3454 kilojoules. Right, that's my energy overall. All right, that's how much energy I get out. So I take how much energy I put in plus how much energy I get out, and I get my overall delta H of reaction. Okay, the overall change in reaction is just going to be the difference between the energies the reactants were at versus where I ended up with my products. Okay, but this is showing the process that it's going through to get there. Now, let's say I get less energy out than I put in. If I get less energy out than I put in, then my products would end up at a higher energy than my reactants, and my delta H would be positive. That would be an endothermic reaction. So we can use these bond energies to predict this delta H of reaction. So to do this, we break all the bonds in our reactants. We get just the atoms. Then we reform bonds to get our products. Now let's look at another example of this. All right, so this time let's look at taking methane, CH4, and reacting it with Cl2 gas. And we get CH3Cl plus HCl. Okay, we want to calculate delta H of reaction for this. Right, so just like last time, we need the Lewis structures. We need to know what bonds we're dealing with. So my Lewis structures, CH4, carbon with 4 hydrogens around it. Cl2 is a chlorine-chlorine single bond. CH3Cl is carbon with 3 hydrogens and 1 chlorine around it. And then HCl is just an HCl single bond. All right, so then next, I need to determine the bonds broken and the bonds formed and their energies. All right, so let's look at our overall reaction here of our Lewis structures. Now, instead of breaking every single bond and breaking everything up into their atoms and then recombining all those atoms, we can simplify this by just looking at what bonds are actually being broken and what bonds are actually being formed. Right? Where are the changes going to occur? Okay, so when I look at this, really all I'm doing is I'm breaking 1 carbon-hydrogen bond, I'm breaking the Cl-Cl bond, and then I'm forming 1 carbon-chlorine bond and 1 HCl bond. Right? I could break up the other 3 carbon-hydrogen bonds, but I'm reforming them at the end anyways. So why bother putting those in the calculations? There's no need to. So all I'm looking at to see what's actually changing, what's actually being broken, what's actually being formed. Okay, and it's just going to simplify the calculation a little bit. Okay, so I know I have one carbon-hydrogen bond broken, one Cl-Cl bond broken, one carbon-chlorine bond formed, one HCl bond formed. Go to my delta H of reaction. I have my information. Plug everything in. And end up with the delta H of reaction of a negative 113 kilojoules. All right, and if I look at a picture of this one, you can see that all I'm doing is just breaking off that carbon-hydrogen and the chlorine-chlorine and then recombining the carbon-chlorine and the HCl. Okay, so that's just a simplified way of thinking about this. Sometimes you can't do that. Sometimes you have complete rearrangement of those atoms, so you have to break all the bonds initially and form completely new ones at the end. But that's how we're going to use these bond energies to figure out delta H of reactions, to estimate those delta H of reactions.